Okay, so let's start with another support vector machine algorithm. Now here we are using the diabetes data and we want to predict whether the person has diabetes or not. So that is the purpose here. Now here we are going to use the diabetes prediction data, and which comes from the Prima diabetes database, right? And in this, before that, let's clear first. So let us clear the output. All the outputs will be cleared. And now, so in this you can see now all the processes have been cleared. So in this project the objective is to predict whether the person has diabetes or not based on various features like glucose level, insulin, age, BMI, etc., etc. And we use the Pima India database for this purpose, right? Now we can run this. Of course nothing will happen in this. Similarly, all the standard libraries like NumPy, Pandas, Matplotlib, Seaborn, etc. are imported for this, and which are required for the purpose of doing this working. So we can import that with the help of these commands, and the database, the data set is available in this file, that is diabetes -1. This is CSV file, and we are taking into Pima data frame. So that is how we are getting our data from this data file into Pima. So that has been done, and all the libraries have also been imported. Now we want to just print the details. So with this we are getting all these, all the columns, that is pregnancies, glucose, blood pressure, skin thickness, etc., etc., all these columns which are there. Then we are going to print the top 5 rows, that is print head, that is also available here. That is all these columns you can see, and these 3 are unnamed, so that also we will see that how to treat them. Then we are going to have the we want to drop these 9 to 12, the last 3 columns that we have seen in here in this case, which are unnamed. So we can clear them with this code, Pima drop Pima columns 9 to 12, and then access is 1 and in place is 2. So this is how you can write this code to drop any particular. They are not physically removed, but they will not be available for our working. That is the purpose. Now we can do that, and again we can see whether it has been done or not. So we can see the Pima head, and now we can see that those 3 columns have gone. They are not available now. We can see the shape of the data, that is Pima. So we can see that 768 rows and 9 columns now are left with this. Again, some more information about it, Pima info. We can get all these things like whether they are integer or object or whatever it is, and all the columns are available here. Then we can also check the describe part, that also gives the various statistics like pregnancies, glucose, blood pressure, what are the counts, mean, standard deviation, etc., etc. All these details are available to us, which are definitely important for our understanding. Then we are going to check whether any null data is there. If it is there, we have to do something, but we can see that they are all 0, so there is no null data available in the data set. Now our observations are that there are a total of 768 records, 9 features in this data set. Each feature can be either of integer or float data type. Some features like glucose, blood pressure, insulin, BMI have 0 values, which represent missing data, or 0 none. There are 0 nan value. Nan means that not a number values in the data set, and in the column outcome, column 1 represents the diabetes positive and 0 represents diabetes negative, right? So this is whatever we have seen in data, we can say that. Data visualization also is helpful in this. So for that we need the SNS that we have already imported earlier. So we can write this, that count plot x is equal to outcome and data is Pima. That is from where this is the source of our data, and for creating this kind of a count plot, we can write this code, x is equal to outcome and data is Pima. So we can run this and we can create a this kind of a bar graph, right? So we have seen that it is again very helpful. You can see that the count and outcomes are available with this kind of a data. Now we are using import into tools, column is equal to Pima columns, whatever are there. Then PLT subplots we are going to generate. Fixed size is 20, 15, that is the size of the graph. Length is length column, whatever number of columns are there. And for ij, that is these two variables are taken in intertools.zip longest column, range is length. Then we are going to print the PLT subplot length 2, 3 and then j plus 1. Then they increase it, go to the next level. Then again PLT subplot, adjust WS space and with the wide space and the horizontal space 0.5, and then the PIMA histogram we are going to generate, and bins is equal to 20 and plot title is I. And so we can get the graph with the help of this. So once you run it, you can see that now you are getting a histogram, and these are available in this fashion. So all these like pregnancies, then glucose and blood pressure, all the individual whatever variables that we have, 8 variables that we have selected, all of them are available in different forms. So we can, just by looking at this, the analyst can easily understand and decide that what is the tendency, what it speaks, what is the purpose of this. Just looking at this, one can do all that. Then we are going to create a pair plot, and again we are using the SNS pair plot data PIMA, again the data frame and then plot show. So once we do this, we again get a graph with the help of this code that we have written, and we can see that how useful this graph would be, so that we can draw some conclusions from this. We can make our own inferences with the help of this kind of a outcome, which is coming with the help of this code that we have just written. Code is simple. You can see there's just 2 lines and hardly any code in this. PLT show is nothing. Then SNS pair plot is common, the plot that we want. It comes in pairs. That is why the name given as pair plot. And database is of course PIMA. That is the data frame that we have used. And hue is outcome. Right. So that is how you are going to get a very colorful kind of a graph, and that is going to be very useful for our purposes. So you can see that the graph has come, and it is very attractive kind of a graph, giving different colors and giving different kind of a meaning. And again you can see all those variables that we have seen, we have selected, all are available here, both in vertical side and in the horizontal side, that is x-axis and y-axis, right? So this is the way you can generate this kind of a graph. Then we are going to generate a heat map. We can create a heat map, and that is possible with the help of this code, that is SNS heat map PIMA.C correlation, annotation is true, and then PLT show, because we want to see the correlation between the 2 variables. So that is the purpose of this. So we can run this, and then you can see that we have got a good heat map along with the annotation inside the cell. And all these 8, that is pregnancy, glucose, blood pressure, skin thickness, insulin, BMI, all these things are available both in the y-axis as well as on the x-axis, right? So again it is very useful for the analyst, whatever you want analysis that you want to draw with this. Now our observations are that the count plot tells us that the data set is imbalanced, as the number of patients who don't have diabetes is more than those who do. So it is very important that the data should always be balanced. Balancing and imbalance means that the data should be, if there is a big gap, that means the people who have the diabetes are just 5% and the people who do not have are say 95%, then it is not balanced data. So that must always be kept in mind, because then your conclusions, your say analysis may not be very accurate. So that is the purpose of it. Then next is that from the correlation heat map we can see that there is a high correlation between outcome and glucose, BMI, age, insulin. We can select these features to accept input from the user and predict the outcome. So that is another the observation that we have got from this. So we can run this. So nothing will happen, of course. Then we are going to go for the data pre-processing, and for that we are going to use all these columns which are there in the PIMA data frame, glucose, blood pressure, etc., which is equal to again glucose, PIMA and all those things which are there, and replace all the zeros and the nan. Nan means not a number, right? You replace all of them, right? Count of nan, and then pima is null dot sum, and then you can also get this number. So when we run this, you can see that pregnancies are 0, glucose are 5, blood pressure, so you can get the complete thing, right? Outcome is also 0, age is again 0. So these are all the things that you can get from with just by writing this code, right? Now you are going to get the top 5 rows with this pima and all that. So these are the 5 rows, and then data set is equal to pima, that you transfer this into data set. Run is again, it has transferred then here in data set. Then you are going to you are going to kind of replace this. So glucose fill Na, data set glucose mean in place is equal to true, because you have to make your that, because we are into pre-processing. So we have to see that wherever there is some kind of a error or something which is not helping us in our analysis, we have to do something for that, and we are doing all these steps here in this. So data set glucose equal to fill Na, that means it is not acceptable data set, then you are going to use the mean in that, and that is that we are replacing. So we are making it true, that means it is to be replaced with this. Similarly for blood pressure, again we are doing this, but there also we are doing the replacement, and in the skin thickness also we are doing this, and the insulin also we are doing it, and BMI also. So these 5 out of this 8, wherever you can see that it is non-zero. Wherever it is 0, it is fine, but wherever it is non-zero, we have to do something, and that is what has been done with the help of this code. Now after doing this, let us run this so that this also gets executed. That has been done, and we are going to see our data now. So data set, now you can see that it is much better than what we had earlier, right? So this is how you can do the pre-processing. Different data has different requirement, of course, but then we should know that how to do the data pre-processing. Now in this data set, the missing values are represented by 0 values that need to be replaced, and the 0 values are replaced by nan, so that the missing values can easily be imputed using the fill Na command. So that has been done. Now we are going to do the feature scaling using min max scaler, right? So now we are going to do the feature scaling. This is also required for the purpose that whether it is if the data is not proper, then we have to do this minimum or maximum scaling. We have to scale it up wherever it is required to scale up, or wherever it is required to scale down. Either of the thing that we can do with the help of this. And this is, there is a library for this, that is min max scaler, and that is available in sklearn. So that also comes under the pre-processing. So all this is done just by one line of code. And here we are going to have the SC, that is and min max scaler. Feature range is equal to 0, 1. Data set scaled, SC fit transform data set, and data set scaled. Now here we have scaled it, so we can get an output into this with the help of this code. And now we perform feature scaling on the data set using min max scaler, so that it scales the entire data set such that it lies between 0 and 1. That is the purpose. It is an important pre-processing step for many algorithms, right? So that is why it has been mentioned also, so that do not skip this. This is very important and helpful. Now we are going to do some kind of a feature selection. So selecting features, that is glucose, insulin, BMI, and age. The X is equal to data set scaled iLock, and this is the way we can select 1, 4, 5, 7. These are the values here, and in Y we are getting the scaled iLock dot values. Again we are getting just 8 only here, and then for splitting X and Y we are using the train test split. We know that it is always required for testing and training. We can do that. Then X train X test, Y train Y test, train test split. XY test side is again 20. That means 20% is kept for the testing and remaining is kept for the training, 80%. Random state is 42. Now this random state means that how many iterations that you want. Now we have randomly taken as 42, but you can take any number and then see the outcome and then decide whether it is to be done again or not. and data set is the outcome. So stratify, that is how we are going to create some stratas. Then print x train shape, print x test shape, y train shape, and y test shape. All these things are to be printed. So we run this, and after running this we get the outcome as this, that is the entire data set has been divided, and train shape is 614 rows and 4 columns, test shape is 154 and 4 columns. Similarly, y train shape is 614 and y test is 154, right? So this is how you can also be sure that entire data has been taken into consideration. This is another kind of a check. Now in this features correlation heat map, we can observe that glucose, insulin, age and BMI are highly correlated with the outcome. So we select these features as X and the outcome as Y. The data set is then split using train test split and in the ratio of 80 and 20, right? So we can run this, nothing will happen here, but now we are going to have our model. So we can create a model now with the help of the support vector classifier. It is a type of supervised classification model whose objective is to classify the data based on a maximum margin hyperplanes built using support vector. This hyperplane is a decision boundary that classifies between various classes. It is built using support vectors, which are the outliers. The hyperplane which has the highest margin is selected as the decision boundary. So this is again for our understanding, so that before going for creating the model, we must know that what we are going to do. So we can run this. SVCs can classify linear as well as non-linear data using a kernel trick, which implicitly maps the input to the high dimensional vector spaces. This kernel trick converts the lower dimensional features space into high dimensional features space, which is linearly separable. For example, data in 2D may not be linearly separable, but when it is converted to 3D using the kernel function, it becomes linearly separate. Now this you must have seen in the SVM tutorial, where we explained it in detail as to how this can be done. So if you have not done, you can refer that. The next is that SVC has 3 main parameters that differ as performance of the model, which are the kernel, gamma, C. The kernel parameter signifies the types of kernel which can be linear for linearly separable data, or RBF, and polynomial for non-linearly separable data. Gamma parameter is the kernel coefficient. As the value of the gamma increases, it tries to exactly fit the data set, which gives generalization error and causes overfitting. C parameter is the cost of the misclassification of the model. The high value of C gives you low bias and high variance, whereas the low value of C gives you the high bias and low variance, right? So this again, this explanation definitely will be helpful if you go back and refer to the SVC support vector machine tutorial also, and then come back here, right? So we'll run this. Then support vector classifier algorithm from sklearn SVM import SVC. SVC is equal to SVC kernel, and linear, that this is the model that we are using, and random state is equal to 42, that we already mentioned. SVC fit, now we are going to fit the model X train, Y train, and we are going to see that what is the prediction. So that will be stored in ypred. SVC predict X test. Based on this data in X test, we are going to predict, and it is available in ypred. So we can run this, right? So that can be also seen, and of course this is done. Now model evaluation. We have to evaluate whether whatever model that we have built, now whatever logic that we have used, now we have to check that we have to evaluate it. So for that we have to again import the matrix, and from that accuracy also, accuracy score. Then accuracy is equal to accuracy score y test and ypred, and print accuracy. Now we are going to print plus string accuracy into 100, that is percentage. So we can run this, and we can see that 73.3766% is there. that is the accuracy, which is not very good, but definitely that is the kind, and if we want we can definitely improve that. We can again do this, repeat it. Now confusion matrix, from sklearn import confusion matrix. CM is equal to confusion matrix y test and y pred and CM, so that confusion matrix can be generated here, that is 85, 15, 26, 28, right? So this is available, this has been created with the help of this code that we have written here. Now we are going to have a heat map of confusion matrix. So for that we are using this code, SNS heat map PD data frame CM, this data, and annotation is true. So we can again run this and we can get this kind of a heat map. You can see the annotation is also available to us. The same thing which we have got here, 85, 15, 26, 28, the same thing we have got here in this confusion matrix heat map, right? Then we are going to do the classification. So from sklearn matrix import classification report. Now we have to classify that because that is our objective. So print classification report y test y pred. So we can run this also and see that how this the output comes. So precision is equal to the precision, recall, F1 score and support, and accuracy is 73%, macro average is 0.69 and weighted average is 0.73. Now with this kind of a output that we have got, we can say that we have chosen 3 metrics: accuracy score, confusion matrix and classification report for evaluating our model. So after doing this, we can say that 73% is okay, but if you further, it is up to the individual, the analyst or the company who wants to do this. So for them is to decide. If they are not satisfied, they can definitely go for the improvement and may wait for unless you get 90% or whatever. But if you are satisfied, you can accept this figure and you can go ahead. So that is how we can do this support vector machine for this kind of a data. Thank you.